Here we have problem set 29, where we're going to talk about stoichiometry. Stoichiometry is essentially our way of accounting for atoms and molecules in a chemical reaction. Okay, and once we can balance an equation to represent that no mass is created or destroyed during a reaction, that balanced equation becomes a very powerful tool, and we'll learn how to use that here in stoichiometry, as well as in problems at 30 here with limiting reactants. All right, so here we go, stoichiometry. Each of the pairs of images below contains substances composed of two elements, red balls and blue balls. Write a balanced chemical equation describing the reaction taking place in each pair of images. Be sure to indicate the physical states of the reactants and products using the appropriate symbols in parentheses. Okay. Well, here I can see that I start with x and y separate, so just x plus y. And then they combine, and what do we get? Well, this is an x and a y stuck together, chemically bonded, so that's a molecule XY. Now we have to make sure that this is balanced. In other words, that we have the same number of x's on the left as we have on the right. You see 1x there, 1x there, 1y there, 1y there. So this is all balanced. Now a lot of people wonder, well, there's 4 blue balls, 4 y's, so do I need to put a 4 there? No, you don't. Okay, this equation is just simply putting, I should say, no, you don't, and you shouldn't. This equation is just giving us the ratio of things happening. So if I have 1x and 1y, I get 1xy. Now I have 4 x's and 4 y's, so I'm going to get 4xy, but that can just be reduced to this ratio of 1, 1, 1. All right, here with B. Oh, they wanted phases on here too. So X, I'm going to say this looks like a gas. It can be difficult to distinguish between gas and liquid, so I'm just going to call them all gas. Okay, B here, I've got my x's and my y's separate, so I know I have x alone and I have y alone, and those both look like gases to me. And when they combine, I get these molecules, units there, that are in units of an x and a y, but they're in like a solid phase, and indeed that is balanced already, so I'm done. Here my x and my y are separate, okay, in the gas phase, and then when they combine in units of, what's blue, 2y, so you got a y there, and an x, so that gives us x, y, 2. That's that molecule. You got 2 y's and an x, so xy2. Okay, and this also looks like a gas. The problem is, how many of each of these reactants did I need to make this product? Well, 1x is fine, but I needed 2 y's to have a balanced equation, is how we say it. And then here I've got my x's in pairs of 2. That's the molecule on the left. And I have y's in pairs of 2. And when they combine, I get molecules of xy. Okay, so I've got 2 x's on the left, so I need 2 x's on the right. The only way I can do that is to put a 2 in front of there. Then I have to check my y's. I've got 2 y's on the left, and indeed I have 2 y's on the right, so I'm good. Okay, write the following reactions as chemical equations and balance them. Okay, so this is going to test some of our memory of naming. So let's take a shot at it. Solution of copper 2 sulfide. So copper 2 sulfide is that. Okay, and it tells you that it's a solution. That means aqueous. Aqueous means dissolved in water, and that's what we'll take solution to mean. Copper 2 sulfide plus silver nitrate. Silver is Ag, nitrate is NO3, and that's also a solution. They're mixed together and they produce solid silver sulfide, Ag2S, and that's a solid, and a solution of copper 2 nitrate, because NO3 is 1 minus, I need 2 of them to balance my copper 2. All right, that's awesome. And it says it's a solution. Now I just have to balance it. I've got a copper on the left and a copper on the right. Perfect. 1 sulfur on the left, 1 sulfur on the right. 1 silver on the left, 2 silvers on the right. So to balance that, I need a 2 there. Now I have two nitrates on the left and two nitrates on the right. Now in this case, because the NO3 stays together, I can just kind of balance it as one unit. But if that wasn't the case, I'd have to say, well, I have two nitrogens, and here I have NO3 2, so I have two nitrogens. Here I have 2 times 3 gives me 6 oxygens. Here I have 3 oxygens times 2 gives me 6 oxygens, so I am balanced. All right, pentane, which is C5H12 gas, reacts with oxygen, which comes as pentane gas, so gas, reacts with oxygen gas, which is O2, and it forms carbon dioxide, which is going to come out as a gas, and water. This is a reaction for burning or combustion of pentane. Now I have to balance it. I need 5 carbons I have 5 on the left, so I need 5 on the right, so I'll throw my 5 there. I'm going to leave oxygen to the end because it's by itself, so I can just balance it with however many I need. It's not going to affect any other molecules. Whereas if I left carbon on the left, if I left carbon to the end, when I change the amount of carbons, it affects the amount of hydrogens. I don't want to do that. So 5 carbons, I need 12 hydrogens. Hydrogens come in packets of 2, so 6 of them will give me 12. Now how many oxygens do I have? Here I have 10, and here I have 6. That gives me 16 oxygens. Oxygens come in packets of 2, so I can put an 8 there. That gives me my 16. Okay, ammonia gas. Ammonia is NH3, and nitrogen monoxide gas react to produce nitrogen. Nitrogen is diatomic, so it's going to be N2, and water vapor. Now to balance this, I've got 2 nitrogens on the left, I got 2 nitrogens on the right. I have 3 hydrogens on the left, 2 on the right, and I have 1 oxygen on the left, 1 on the right. So this one's going to get kind of tricky. Here I have everything's balanced except hydrogens. And so I'm going to put a 2 here, which is going to give me 6 hydrogens, which means I need a 3 there. Now I've got 6 hydrogens. But now I have 3 oxygens. So here I need 3 oxygens. So if I put a 3 there, now I have a total of 5, 6, 7, 8 nitrogens. And the only way to get 8 nitrogens is to put 5 nitrogens, excuse me. We get 5 nitrogens here. There's a couple ways to do this. First, say nitrogens come in packs of 2. So if I have 5 halves and 2s, the 2's cancel and I have 5 nitrogens. A lot of people don't like to do that though, and so instead of putting a fraction, you'd come here and say, I need 5 nitrogens, but they only come in packs of 2, so I'll double everything. 4, 6, 6. Now I need 10 nitrogens. That's 5 N2s. That's what most people choose to do, to use whole numbers. Even though fractions is not wrong by any means. All right, sodium phosphide, which is Na3P, reacts with water. They don't give me a phase for sodium phosphide. I'm going to expect you to just pull that out of your head. In case you are wondering, though, it is a solid. With water, H2O liquid, to produce phosphine gas, PH3 gas, and a solution of sodium hydroxide, NaOH. Solution will be aqueous. Okay, so I've got 3 sodiums, so I'll need a 3 here for my sodiums. And then 1 phosphorus. Here I have 2 hydrogens, but on this side I have 3 plus another 3 gives me 6. So if I put a 3 here on my water, now I have 6 hydrogens and 6 hydrogens. And I have 3 oxygens and 3 oxygens. So that looks balanced to me. Unless... Yep, that's right. Okay, a mixture of nitric acid. Nitric acid is NO3. Is that right? Nitric acid. And nitrous acid is formed. Oh, so these are products. They just wrote it backwards. So nitric acid, HNO3, and nitrous acid, HNO2, and acids are typically written as aqueous, as in dissolved in water, is formed when water reacts with dinitrogen tetroxide. So dinitrogen tetroxide. I don't know what that is. Let's say it's a solid. Let's say it's aqueous, shall we? Okay, so let's balance this. So I have 2 hydrogens on the left and 2 hydrogens on the right. Awesome. I have 2 nitrogen on the left, 2 nitrogen on the right, and 5 oxygens on the left, 5 oxygens on the right. So everything's balanced, and I'm done. Cool. So there's some practice writing and balancing equations. Oh, we get some more practice. Okay, liquid ethanol. Ethanol is C2H6O as a liquid. Reacts with oxygen. Oxygen is O2. To form carbon dioxide and water vapor. This is another combustion reaction. We're taking this hydrocarbon, adding oxygen, and making CO2 and water. This is balance it. I need 2 carbons, so I'll need a 2 there. I need 6 hydrogens, so I'll need a 3 here to give me my 6 hydrogens. And now I need 4, 5, 6, 7 oxygens. Here I have 1, so I have 6 left, so I put a 3 there. I'll get my oxygens balanced. Calcium and water. Calcium we're going to say is a solid plus water as a liquid. React to form calcium hydroxide, which is CaOH2 because calcium has a 2 plus and hydroxide is a 1 minus. That's a solution. And hydrogen gas. So 1 calcium, 2 hydrogens. Here I have 2 hydrogens plus another 2 hydrogens gives me 4 hydrogens. So that means I need a 2 there. Now I have 2 oxygens and 2 oxygens. So now I'm done. That's nice and balanced. Aluminum. I'm going to say that's a solid. And oxygen react to form aluminum oxide, which, if you balance the charges, is Al2O3. So I need 2 aluminums. I need 3 oxygens, but they come in sets of 2, so I could do 3 halves. Or I could do 4 aluminum plus 3 oxygen goes to 2 Al2O3. Either of those is good. Solutions of lead to nitrate. So lead to nitrate and phosphoric acid react to produce solid lead 2 phosphate and a solution of nitric acid. Okay, I got 1 lead here and 3 there, so we need a 3 there. Now I have a nitrate times 2 times 3 gives me 6 nitrates. Well, nitrate is right here, so I'm going to need 6 of them. Okay, I have here I have 3 hydrogens, here I have 6. So I'm going to need a 2 there to give me my 6 hydrogens. I have 2 phosphates, everything is balanced. 3, 2, 1, 6, yep. Alright, and lastly, phosphorus, P4, burns in air to give diphosphorus pentoxide, which we're going to say is a gas. I have 2 phosphorus, here I have 4, here I have 2, so I need a 2 there, which gives me 10 oxygen, so I need 5 there. Awesome, even more practice. Alright, some scientists believe that life on Earth originated near geothermal vents. Balance the following reactions, which are among those taking place near such vents. All right, let's do it. Here I have 2 sulfurs. Here I have 1 sulfur. Here I have 2 sulfurs. So I'm going to need a 2 there to balance my sulfurs. Here I've got an oxygen and 1 oxygen. So I'm going to just guess right now that those are 1. See how everything else works out. Okay, and carbon. So here I have 1, 2, 3 carbons. 1, 2, 3 carbons. And hydrogens, there's 4 times 2 is 8. And here we have 1, 2, 3, 4, 5, 6, 7, 8. Awesome. So we are balanced just like that. 2, 1, 1, 1. And now the second one, 2 hydrogens, 4 hydrogens. I'm going to put a 2 there. And if that was a 1, we'll see if we need to change it later. Okay, and then, oh, you know what? We're definitely going to have to change it. Let's get rid of those because we have this S8. So let's start there. S8, so I'm going to need 8 here for those sulfurs, which gives me 16 hydrogens, and these come in sets of 4, so I'll need 4 of these molecules to give me my 16 hydrogens. And that gives me 8 carbons on the right, which means I'll need 8 carbons on the left. I can check my oxygens. I have 8 oxygens here, and 4 times 2 is 8 oxygens there. Awesome. You don't need to write 1 when you're balancing. You can just leave it. Let's balance these guys. 1 sulfur, 1 sulfur. Awesome. So here we have 3 oxygens. Here we have 2 and this guy. So if I did a 1/2 there, that would give me 3 oxygens on the left and on the right. But instead, I'm going to double it. 2, 1, 2. All right. Here I have 1 sulfur, 1 sulfur. Awesome. And so 3 oxygens on the right. So I would need 3 halves here, but I'm going to double it, which is going to give me 3. So I have to double all of these. I think. Let's see. So right now I have 2 sulfurs on the left, 2 sulfurs on the right, 4 hydrogens on the left, 4 hydrogens on the right, 6 oxygens on the left, 4, 8. Let's see, what am I missing? Oh, I don't know why I multiplied that by 4. Should multiply it by 2. There we go. So 4 hydrogens on the left, 4 on the right, 2 sulfurs on the left, 2 on the right, 6 oxygens on the left, 4, 6 oxygens on the right. Okay. This last one, we've got 8 sulfurs there. The problem is there's 2 places with sulfurs. I don't know which one to deal with first, so I'm just going to leave it. I'm going to say, let's see, I got my 2 hydrogens, 2 hydrogens, 2 oxygens, 1 oxygen. So I'm going to throw a 2 there, which gives me 4 hydrogens. And if I want 4 hydrogens, I need a 2 there. That gives me 2 sulfurs. My oxygens, though, are good right now. My sulfurs are not. So if you look, I have 2 oxygens there, 2 oxygens there, so that's fine. But my sulfurs are messed up, and so I can't change this sulfur to match this one because it'll screw up my oxygens. So as a trick, I'm going to double and see what happens there. If I do a 4 there and a 4 there, see now my hydrogens are good. My oxygens are not, though, because I have 4 oxygens on the right and only 2 on the left, so then I can put a 2 there. But now I'm missing 2 sulfurs because I have 8 on the right and only 6 on the left. So I'm just going to double again and see what we do. And if you double too far, that's fine, because at the end you should notice that you can just reduce all your numbers if they're all divisible by 2 or something. All right, so now let's see, my hydrogens, I have 16, 16, oxygens 8, 8, sulfurs 8 plus 4. 8 plus 4 is 12. So if I want 12 sulfurs here, that would be 12 over 8, which is the same as divided by 3 gives me 4 over, hold on, 12 over 8 divided by 4 gives me 3 over 2. To get rid of that fraction, I just double everything. 16, 8, 3, 16. So now 32 hydrogens, 16 sulfurs, plus 8 gives me not 16, but 24 sulfurs, 24 sulfurs, 16 oxygens, 16 oxygens. And if you think that's high and that seems unreasonable, well, then you can just say, well, I know everything's balanced. I just looked at it, and there's no way that I can divide these and get to smaller integers. So that's what tells me M10. Okay, potassium chlorite, KClO3, is used in the oxygen supply systems of aircrafts, submarines, space stations, because heating KClO3 in the presence of MnO at catalyst causes it to decompose and produce O2 as follows. Let's balance this guy. I left a lot of space to balance. K. My K's are good. ClCl, O3, O2. So I would need a 3 halves there, but I'm going to double it. If I have a 2, 2, and a 3, now I've got 2 potassiums, 2 potassiums, 2 chlorines, 2 chlorines, 6 oxygens, 6 oxygens. Okay, and this is the point at which balanced equations start becoming a very useful tool. So let's talk a little bit about what this equation tells us. Now, this equation is balanced for molecules of each of these components. So 2 molecules of KClO3 produces 2 molecules of KCl plus 3 molecules of O2. In other words, 2 molecules of KClO3 equals, let's say, 3 molecules of O2. We've now created this conversion factor. What it allows us to do is, for this reaction, if we have some amount of KClO3, we can convert that into some amount of O2. And we'll get the opportunity to do that. But we don't usually like working in molecules because molecules are really small. We like working in moles. But if we take each of these numbers and multiply it by Avogadro's number, we get not multiply, divide by Avogadro's number. Then we get 2 moles of KClO3 equals 3 moles of O2. And that's what we'll use most of the time, is in the units of moles. But let's see what this looks like. KClO3 is also often used to prepare small amounts of O2 on the spot in high school chemistry labs where keeping a full tank of oxygen is impractical. How many grams of O2 can be prepared from 4.5 grams of KClO3? All right, we've got 4.5 grams of KClO3. We're going to convert it into O2. Okay, so the indicator that this problem requires a balanced equation is that they give us an amount of one substance and ask for an amount of a different substance. And because of that, we're going to need some relationship between KClO3 and O2. Fortunately, we have it in this balanced equation. We know that 2 moles of KClO3, because that's 2, equals 3 moles of O2. There's a 3 there. And we're going to exploit that relationship in order to convert from the world of KClO3 into the world of O2. But if you remember, that relationship is in moles. And so we can't use it with 4.5 grams of KClO3. We need to convert that to moles. And we know how to convert from grams to moles using a molar mass. So if I pull up the periodic table, maybe, come on, there we go. All right, I got to find the molar mass of KClO3. So I'm going to take potassium, 39.98, plus chlorine, plus 3 oxygens, and I get a molar mass of 122.5 grams. Now I'm in units of moles of KClO3. I'm trying to get to oxygen, though. Well, I know in this reaction, 2 moles of KClO3 gives me 3 moles of O2. So 2 moles of KClO3 gives me 3 moles of O2. Now I might be done. I'm in moles of O2, but it wants grams of O2. So I need to do one final step and say 1 mole of O2 is 32 grams. Now it becomes a good skill at this point in the course to start making sure you write down not just grams, but grams of KClO3, because now we're switching between different species and you can get really turned around. if you skip that part. So I've got 4.5 divided by 122.5 times 3 over 2 times 32, and that gives me 1.76 grams of O2. In other words, if you were to react 4.5 grams of KClO3, you could get 1.76 grams of oxygen out of it. Okay, we're going to do this again and again and again. In a self-contained breathing device used by first responders, potassium superoxide, KO2, reacts with exhaled carbon dioxide, producing potassium carbonate and oxygen. Balance the equation. So 2 potassiums here, so let's throw a 2 right there. Let's see, 1 carbon, so let's put a 1 there, which leaves me with 2 6 oxygens. I've got 3 oxygens here already, so I need 3 more, so that's going to make that a 3 halves. But I'm going to double it to get rid of the half. So let's just double check. 4 potassiums, 2 carbons, 2 carbons, 8 oxygens plus 2, that's 12 oxygens, and here's 12 oxygens. All right, so we are balanced. How much O2 could be produced from 85 grams of KO2? So we're going from KO2 to O2. We're jumping from the world of one molecule to a different molecule, so we need a relationship between them. This balanced equation gives us that relationship. So we're going to start with 85 grams of KO2. Okay, and we got to get to moles if we want to use the balanced equation. So let's get to moles. 1 mole of KO2 is 71.10 grams. Now I'm in moles of KO2, and the balanced reaction tells me that 4 moles of KO2 makes 3 moles of O2. And how much O2 could be produced? That doesn't specify grams, so we could just solve this in moles and be done with it. Make that line a little bit shorter. Okay, 85 divided by my molar mass times 3 divided by 4, and that gives me 0.897 moles of O2. Okay, so we use the balanced equation to jump from the realm of KO2 into the realm of O2, because we knew 4 moles of KO2 makes 3 moles of O2. Let's keep going. Safety airbags in automobiles inflate when a sudden jolt causes a spark to hit a pocket of white sodium azide powder, which rapidly decomposes into elemental sodium and nitrogen gas, which fills the airbag. So the nitrogen gas is filling the airbag. Balance equation. All right, 1 sodium, 3 nitrogens. I'm going to double it. Now I have 6 nitrogens, so I can throw a 3 right there. Get nice whole numbers. How many grams of NaN3 are needed to inflate an airbag to 36 liters with a pressure of 1.15 atmospheres and a temperature of 26 degrees Celsius? Okay. We're trying to get NaN3 from how full we want to fill our airbag. Well, what fills up our airbag? Nitrogen gas does. So this is information about the nitrogen gas. Okay, so we know we're going to need this balanced equation because they're giving us information about nitrogen gas, but they're asking for information about NaN3. And if we want to use the balanced equation, we have to be in moles. So the question is, how do we get moles of N2 from the information they gave us? Because once we get there, we can jump from N2 to NaN3 using their equation. Well, they give us a volume, a pressure, and a temperature, and you should be familiar with the fact that PV equals nRT, so if they give us a volume, a pressure, and a temperature, we can get moles, no problem. So let's do that. So moles is going to equal PV over RT, pressure is 1.15, volume is 36 liters, 0.08206 is the ideal gas constant, 26 degrees Celsius is going to be 299 Kelvin. So I plug that in. And I get 1.69 moles of N2. That's what's filling the airbag. So how much NaN3 do we need to react in order to get that much N2 so that we can fill up our airbag to those conditions? Well, 1.69 moles of N2. The equation tells me that 3 moles of N2 comes from 2 moles of NaN3. And then lastly, they want grams, and so I know that 1 mole of NaN3, now I got to get my molar mass of NaN3. And I get a molar mass of 65.01 grams. Which, when I plug all that in, maybe 1.69 times 2 over 3 times 65.01, and I get 73.24 grams of NaN3. Sorry for my hand. Okay, so again, we needed to get NaN3 information from nitrogen information. In order to do that, we needed to get to moles, which in this case required the ideal gas law. And then we could use stoichiometry. All right, nitrogen triiodide is a contact explosive, meaning it explodes literally at the touch of a feather, producing a loud, sharp snap and a purple cloud of iodine as follows. Let's balance this equation. 2 nitrogens, so 2 nitrogens. If I put a 1 right there, that gives me 6 iodines, and now I have 6 iodines there. Balance equation. If you want to produce 10 liters of nitrogen gas, how much NaN3 must you start with? The density of N2 is 1.25. So we want to make 10 liters of nitrogen gas. So they're giving us information about nitrogen, asking for information about NaN3. Those are 2 different species, so we know we're going to need to use this equation. If we want to use this equation, we've got to get into moles. So we want to make 10 liters of N2. We've got to get into moles. Okay. And they tell us 1 liter of N2 is 1.25 grams. So this means 1.25 grams per liter. 1.25 grams per liter. Then we got to get into moles if we want to use the equation. We know that 1 mole of N2 is going to be 28 grams. And now that I'm in moles of N2, I can apply this equation. The equation tells me 1 mole of N2 comes from 2 moles of Ni3. And just for the heck of it, in this case, let's go all the way to grams. So 1 mole of Ni3 is going to weigh, nitrogen is 14.007 plus 3 iodines, 126.9. That's a molar mass of 394.7. Okay, I can plug all that in my calculator. Which gives me 352.4 grams of Ni3. So in this case, in the case up here, they told me like a volume of gas I wanted, and they gave me information so I could use the ideal gas law to get moles. Here they gave me a volume of gas that I wanted, but they gave me a density, which allowed me to get into grams, and then I could get into moles. Okay, but remember, if I'm trying to switch from one species to the other, I need to use an ideal gas, or I need to use a balanced reaction, and so I need to get to moles. However that is, there's different ways, but however it is, I need to get to moles. Okay, the first step in the industrial production of nitric acid is reacting ammonia with oxygen according to the unbalanced equation here. How many liters of NH3 at that 850 degrees Celsius, 5 atmospheres are required to react with 32 grams of oxygen? Okay, so they're asking about NH3 and giving us information about O2. They give us some information about NH3. You'll see how we use that. But it's not enough. Our final answer is in terms of NH3. And they give us information about O2. So we need to balance this reaction. 1 nitrogen, 3 hydrogens, not 3 hydrogens. But if we, let's see, and 2 oxygens. So I'm going to double, do a 2 there, and a 2 there, and a 2 there, which now gives me 6 hydrogens. That's 6 hydrogens. But that's now 5 oxygens and 4 oxygens there. That's not going to work, so let's double it again. If I have a 4 nitrogens, I need 4 nitrogens there. 12 hydrogens, now I have 12 hydrogens there. And now, let's see, 6 oxygens, so that's 10 oxygens, so I need there 5, gives me my 10 oxygens. Cool, nice and balanced. All right, react with 32 grams of oxygen. We know we want to react with 32 grams of oxygen. We want to find liters of NH3. They give us a temperature and a pressure. If they give us a temperature and a pressure and they want liters, we need moles, and then we can get liters, right, from the ideal gas law. Well, we can get moles of my NH3 using stoichiometry and my 32 grams of oxygen. So we got 32 grams of oxygen. I'm trying to get moles of NH3. If I want to use this equation to get from oxygen to NH3, I need to get to moles of oxygen. I know one mole of oxygen weighs 32 grams. And the equation tells me if I want to react 5 moles of oxygen, I'm going to need 4 moles of NH3. So just as we could convert from one reactant to a product, and it tells us how much product do I make with that reactant, I could also convert between 2 reactants, and it tells me how much reactant do I need to totally react the other reactant. Okay, in this case, how much NH3 do I need to totally react 32 grams of oxygen? Okay, and when I do that, that gives me 0.8 moles of NH3. But they don't want to know about moles of NH3, they want liters of NH3. So I've got my amount of NH3, but I've got to get it from moles to liters. They give me information so I can use the ideal gas law. PV equals nRT, so volume, liters, is going to be nRT over P, 0.8. Ideal gas constant, 850 plus 273 is 1123 over pressure, 5. Okay, and when I do that, let's see, 0.8 times 0.8, 206, times 1123 divided by 5. There we go. And that gives me, I need 14.7 liters of NH3. Okay, so in this previous one, we used the ideal gas law to get moles, and then use those moles to do stoichiometry. Here we use stoichiometry to get moles, and then use those moles in the ideal gas law. Okay, but the only new thing here is this jumping from one species to another using a balanced equation. All right, let's keep going. 0.811 grams of KClO3 is decomposed as follows. The O2 is collected over water. Now let's talk about what that means. That means I have my reaction vessel. I run my reaction in here. O2 gas comes out, and we dip the tube under water. and the bubbles bubble up. I'll make the water blue. Okay, and so up here is my O2 gas coming out of my reaction. And that's collected at 28 degrees Celsius at 765 torr. What's the volume of water displaced in this measurement? In other words, what's the volume of this space, assuming the reaction goes to completion? So this is very similar to the last problem. Okay, they gave us a pressure, they gave us a temperature, they asked for a volume. Well, then I need to find the moles of O2 that's going to fill that space, that's going to come out of this reaction. Well, I know I started with 0.811 grams of KClO3. Okay, and I'm trying to get moles of O2. Well, 1 mole of KClO3, I think I found the molar mass in an earlier problem, didn't I? KClO3, 122.5. Okay, and the reaction tells me that 2 moles of KClO3 gives me 3 moles of O2, which then tells me that I get how many moles of oxygen from that reaction? 0.00993 moles of O2. All right, so you might think now, I have a temperature, I have a pressure, and I have these moles, so I can find volume. Okay, and there's actually one little intricacy in a problem like this where you're collecting your gas over water that we need to talk about. We know that oxygen gas is in this space, okay, but if you remember talking about vapor pressure, that told us anytime you have a liquid in anywhere, okay, with air above it, some of those liquid molecules break into the gas phase, which means not only do we have oxygen in this space, we also have some water molecules up here. So while the total pressure in here is 765 torr, not all of that comes from oxygen. The pressure from oxygen is going to be a little bit less because some of that pressure comes from water. Now, without looking up, there's no way from this problem to know how much of the pressure comes from water. But what you would look up is you'd look up the vapor pressure of water at, in this case, 28 degrees. And if you look that up, you'd find that the vapor pressure for water at 28 degrees is somewhere around 28.35 torr. All right, well, we're trying to find, we have here the moles of oxygen. If we want to use the ideal gas law with the moles of O2, okay, we're only going to get the pressure of O2. Or in other words, if we want to get, if we want to use the moles of O2, we need to use the pressure of O2. It doesn't make sense to use the moles of O2 and the total pressure. Well, we know this is the total pressure, this is the pressure from water, and so the pressure from O2 is just whatever's left. So 765 minus 28.35. So the pressure of O2 is 736.65. And that's what we get to put into the ideal gas law. So we now have the temperature of O2, the pressure of O2, and the moles of O2. And we're trying to find volume. We have our moles, ideal gas constant, and the temperature is 0.1 for my pressure, but just the pressure of O2. It's 736.65, but I need it in atmospheres, so I'm just going to divide by 760 right there to get it in atmospheres. And when I do that, I get my volume equals, 0.253 liters. So after I run that reaction with 0.811 grams of KClO3, the gas, the oxygen collected underneath, fills up 0.253 liters. Now, let's kind of review what we did here. So, we knew our amount of KClO3 we were reacting, and so we could use that to get the moles of oxygen after the reaction. But we don't want the moles of oxygen, we wanted the volume. And so since they give us temperature and pressure and we found moles, that implies that we should use the ideal gas law. The problem is, when you collect a gas over water, you get the gas that you're collecting, but you also get some water vapor because of the vapor pressure of water. So you can look up the vapor pressure of water at the temperature you're at, and you need to subtract that pressure out of the total pressure. That gives you your pressure of just the gas. And then we just use the ideal gas law with the moles of O2 in this case, the pressure of O2, and that gives us the volume. All right, what do we got left? Oh, this is it. In rocket fuel, as in many of the balloons we blow up in class, hydrogen gas reacts with oxygen, O2, to form water vapor. So we got hydrogen gas plus oxygen gas. This is another combustion reaction. We're adding oxygen. Make water vapor, not liquid. Okay, so I've got 2 oxygens, so I need 2 oxygens there. Now I have 4 hydrogens, so I need 2 H2s. Suppose you have a mini rocket and access to 25 liters of oxygen and 4 liters of hydrogen gas. If you use up all the gas possible blasting off your rocket, how many liters of water vapor did you produce? Okay, so we've got 4 liters of hydrogen, 2.5 liters of oxygen. We need to figure out how much water we produced, how many liters of water we produced. Now, they give us liters. Now, we talked about if I'm trying to take my amount of hydrogen and convert it into water, I need to get to moles. And that's true. But in this case, they don't give us any way to get to moles because they just give us a volume. They don't give us a pressure and a temperature. They don't give us a density. Okay, so how do we get to moles? And the trick is we don't actually have to in this case, because if you think of it, if you had moles and you wanted to get, if you had volume and you wanted to get that volume into moles, you would multiply by P and divide by RT. But then you'd get that moles and you convert it to your moles of other thing, and in order to get into volume at the end, you would multiply by RT and divide by P. And so because the ideal gas law tells us that at the same temperature and pressure, two gases of this at the same temperature, pressure, and moles, two gases will always occupy the same space. Or another way to put that is, at the same temperature and pressure, 1 mole of gas A will always be the same volume as 1 mole of gas B. What that means is that here, these numbers mean 2 moles of H2 plus 1 mole of O2 gives me 2 moles of water. It also means 2 liters of H2 plus 1 liter of O2 gives me 2 liters of water. And that's only true because all of these are gases. It's really only true because we're assuming all of these are ideal gases. And so they change at the same temperature and pressure, they're going to take up the same volume per mole. So what that means is we can say my 2.5 liters of oxygen, let's figure out how much water that would make if I just reacted my 2.5 liters of oxygen. I know 1 liter of oxygen gives me 2 liters of water, so that could make 5 liters of water. Hey, but what about my 4 liters of hydrogen? Well, 1 liter of water comes from 2 liters of hydrogen. So my 4 liters of water or of hydrogen will only make 2 liters of water. Okay, as a result, hold on, did I do that wrong? Yes, 2 liters of water comes from 2 liters of hydrogen. Okay, so that's going to make 4 liters of water. So I'm going to react my oxygen and my hydrogen. If I just had oxygen with unlimited hydrogen, I can make 5 liters of water. if I just had hydrogen with unlimited oxygen, I can make 4 liters of water. So which one am I going to make? I'm going to make the 4 liters because I'm running my reaction. Once I make 4 liters of water, my hydrogen's gone. And so I'm never going to get this high because my hydrogen runs out and my reaction stops. We'll talk about this in the next video, but this is called a limiting reactant situation because my hydrogen runs out first. We call it the limiting reactant. My oxygen, because there's some of it left over, we call it the excess reactant. But there we go. How many liters of water vapor can you produce? 4 liters. How many grams of water vapor did you produce, assuming we're at standard temperature and pressure? So now, if they give us a temperature and a pressure, and we have a volume, so we can get our moles of water. Trying to get moles is PV over RT. Standard pressure is 1 atmosphere. Standard temperature is 273 Kelvin. Oh, that's volume, sorry. 4 liters. 0.08206. And standard temperature is 273 Kelvin. And when I do that, let me just double check my math. 1 atmosphere times 4 liters divided by 0.08206 divided by my 273 Kelvin. Oh, man. Gives me 0.179 moles of water. But I don't want moles, I want grams, and so then I can just say, well, with water, I know that 1 mole of water is 18 grams. So multiply that by 18, and I get that I will produce 3.21 grams of water from this reaction. Okay, so what's the key here? The key in this problem set is understanding that when you have a balanced reaction, you have a relationship between all the different species in that reaction. Okay, and these are molar relationships. And so if we're given a problem where we start in units of SO2 and we want to go to SO3, or we start in SO2, we want to go to O2, okay, we have this relationship that says 2 moles of SO2 and is equal to 1 mole of O2. Okay, and we exploit that relationship to run these calculations. And that is problem set 29.